Hello and welcome back to section 20. In this video we'll be going over example 2, which shows how to use superposition of power to calculate average and RMS values for signals that are written out. So superposition of power is this neat concept that we have these common transformations for DC, sine, square, and triangle. So again, a DC signal is what we've been working with. It's just a flat line. A sine wave, you know what a sine wave looks like hopefully. A square wave will go up and then down and up and then down, and it might be bounded at 0 or it might go above and below 0, depending on what you want to look at it as. And a triangle wave, that's what your group problem was if you did the group problem. So that's a triangle wave. So let's look at this. So we're going to find the DC and RMS voltage for this signal. V of t equals 5 plus 4 cosine 5t plus 4 cosine 10t. And so we could integrate this, but that's not ideal. So the first thing we want to find is VDC. So think about it this way. This 5 volts, so if I kind of draw each piece of this 5 volts is up here at 5. This cosine function is going to oscillate above and below 0. So it'll have some area above, some area below, but it'll average out to 0. This cosine function will do the same thing, same magnitude, just going to be slower, but I don't really care about that because it's going to average out to 0. So basically, if I go and I do the DC portion of this, it's only caused by this piece right here. This is the DC voltage, the piece that doesn't have the cosine function in front of it. So VDC is just 5. Really easy to find. RMS is a little bit trickier, and this is where we're going to get into superposition of power. So superposition of power states that V RMS squared is equal to the summation of the T over T, sorry, I go subscript end on this, of the VRMS of the nth signal squared. So basically take up all your signals, square them, multiply them by how much of the cycle they take up. So if they take up the entire cycle, it'll just be capital T over capital T, but if they're like half of the time, then it'll be like 1 over 2 or something like that. And then you're actually going to square root this side, but it looks cleaner if you put the square on this side. So really, you could write it a different way if you really wanted to. So something like that if you really wanted to. But I prefer this one. So this is nice because we could then evaluate each of these individually. It gets even better if we use these shortcuts, these predefined, because these are the common signals you're going to see. DC signals, square waves, triangle waves, and sine waves. These are basically everything you're going to see, like 90% of the stuff. It's going to be this stuff. So let's try that with our signal. So we have, let's move this down here and just do it real quick. We have V of t equal to 5 plus 4 cosine 5t plus 4 cosine 10t. Now there is a caveat with this. These signals have to be orthogonal. Really all that means is that the frequency here and the frequency here don't match. If they matched, you would just add them together anyway, so it wouldn't be that big of a deal. But just a note, they must be orthogonal. It's typically not a problem that we run into. Alright, so this is a DC signal. So here, I'll keep it this way. So our DC signal, the VRMS of this is just the magnitude, so it's just going to be 5. And we're going to square it per the equation here. So V RMS squared is just going to be 5 squared plus. So this is going to be a cosine function, which is also a type of sine function. So it's going to be the magnitude divided by 2. The magnitude is 4, so we're going to go 4 over root 2. We're going to square that entire thing. If it helps you, we can make this in a quantity as well. Over here, we know that these are orthogonal. Again, if they weren't orthogonal, I would just add them together because they'd both be like 5t or 10t. I get the same thing, 4 over root 2, square the entire thing. VMR squared, so you get 25 plus, this becomes 16 over 2, which is 8. This becomes 16 over 2, which is 8, which is 41. And VRMS just becomes the square root of 41, which is 8. Sorry, 6.403. And I challenge you to try to do that faster with integration. All right, so hopefully that helps. You now have a nice shortcut to find the RMS without having to do the integral. If you have any questions, please let me know.